So last time we talked about the growth of snow crystals in air and looked at this matrix of different shapes. And what I didn't tell you the other day was that this is a starter matrix. We've got a new matrix, so you can really see things in even more detail, going from minus half a degree to minus 24, and sort of a logarithmic progression here, and you can really see the transitions from plate-like crystals over here to needles and needle-like dendrites, and then plates again, and plate-like dendrites around minus 15, and then over here it gets more columnar. And our goal is to really understand this entire matrix, okay? So that means we need to understand the physical processes that are driving all this, and it's a complex picture because there's a lot of things going on. And if we understand it, then reasonably well, we should be able to make quantitative computer models. And if that works, then the idea would be to reproduce this entire matrix just using a single computer model that can produce diffusion limited growth in any temperature. So you just give me the temperature and supersaturation and run it, and we would hopefully see things that more or less agree with experiments. So that's a goal. This has not been achieved by any stretch of the imagination yet, but we're getting there. We're starting to understand the physical processes. We're starting to get computer modeling working, and so we're making some progress. And the first step, which I talked about in the first lecture, was diffusion limited growth. So that's physics is pretty well understood. It's mostly particle diffusion. We mostly ignore heat diffusion. It's less important. It's not always negligible, but particle diffusion is the big player. And so for that, the underlying physics is well understood. It's a diffusion equation, in fact, even the Laplace approximation. So it's a very simple equation. It's very easy to write that into an algorithm that will solve the diffusion equation. That's been known for many, many years. And so, and that produces branching and complex structures, diffusion limited growth. And so that kind of explains the vertical axis here, in that we start out with simple faceted structures, and as you turn up the supersaturation, diffusion limited growth becomes a more dominant factor, and so you get very strongly dendritic structures. This is also true in size. If the crystals are bigger, then diffusion limited growth is more important than faceting. But mostly we don't get really large, so we're not talking about anything too big. So the variable is supersaturation. And although the physics is easy to understand and it's easy to code up, it nevertheless can be pretty hard to solve for complex structures, so dendritic structures. And we'll talk about that in the third lecture, but it's when you have a combination of faceting and branching. Those are two things that don't go well together in computer models, and so it's a little tricky. So that has been a difficult problem to solve the diffusion equation and get both branched and faceted structures. People have been able to produce branch structures over the years, but not yet both, not very well. So there's that. The second step, which I'm going to talk about today, is the attachment kinetics. Those are the two big players, is particle diffusion and the attachment kinetics. And for that, we focus on this parameterization in terms of an attachment coefficient, alpha. And that's where we just dump all of the physics. The rest of this is just scaling. And all of physics is in this attachment coefficient, which depends on temperature and supersaturation. And so we have to try to understand that. The underlying physics here is not at all well understood. It's quite poor. Generally, we know some of it, but not all of it. It involves the molecular dynamics of what's going on the surface, of course. That's where the attachment kinetics is really just the dynamics of how the crystal grows. And that is not a simple problem. It involves lots of particles and sort of a collective behavior of lots of particles. And this is responsible for faceting, of course, and also the large-scale morphological anisotropy, namely plates and columns. If you see plates, thin plates, or like these, or columns that are needle-like structures, that tells you that the attachment coefficient, the attachment kinetics, is highly anisotropic. And so the puzzle here is that it changes it. So they're highly anisotropic here to make plates, anisotropic in the opposite direction here to make columns, and the opposite direction again to make plates, and then far over here more columns. And so it's this changing anisotropy with temperature by a large amount. Okay, so it can be 100 to 1, and then 1 to 100 and 100 to 1. It's really a puzzle. And that explains that the attachment kinetics is really responsible for the temperature axis. Yeah, sure. Like when you're in here, like this cup, and these things near the cups, the crystals are kind of growing at about 45 degrees, so they're roughly the same. But the transitions are pretty abrupt. But there are intermediate states. Well, we're getting to that. For now, we're looking at observations, but that's the challenge, is to explain that. And it's not easy, I will give you that. So we have to really look at the molecular dynamics of crystal growth. And the ice surface is a complicated place. There's a lot going on. And we're going to do what condensed matter physicists do, is we try to take a very complex problem involving 10 to the 18th particles all moving in concert, and we try to reduce it to some fundamental essence. So we want to go from this very complex thing to something of a few brushstrokes that we can kind of understand. You can't always do that, of course. If you look at, say, turbulent convection, you don't have this. You can't do this very well. But we're going to try as best we can for crystal growth. Okay, so we have this equation where we have the velocity. This is really just a definition of variables. There's not much physics in this equation. The only physics is in this kinetic velocity, which involves some statistical mechanics. And that is just if for low growth rates and if alpha is 1, then we can calculate the growth pretty easily. And so we factor that out and put it into this number, which is just kT, mass of a molecule, and the saturated vapor pressure of ice. And this is the number density. So that's just the density of ice solid. Okay. Well, sigma surf is a parameter. That's just an external parameter. So we apply a surface supersaturation, and the crystal will grow. Okay, and so this is just an applied variable. This is just a number, and alpha is just telling you what's going on. It makes the crystal grow. Okay, so again, that's just a parameterization. And the reason we do this is because now we have some simple special cases. Like if you have a liquid water surface, then alpha is 1 or close to 1, and that just means that any impinging molecules, water molecules that hit the surface, are just immediately incorporated into the surface. Okay, and so what that means is that if the supersaturation is 0, the velocity is 0, and as you increase the supersaturation, you can just easily calculate. You've got a vapor pressure of the surface and a vapor pressure that's applied, and that gives you supersaturation, and the growth just goes. It's very, very simple. And we know the physics there. The boundary condition is simple. And similarly, if you have what's called a rough ice surface, same story. And to make a rough ice surface, you just have to have a lot of these molecular steps. Because the idea, which seems to be true, is that molecules that hit those steps, those are one molecule high steps, they can attach very easily. There's a high sticking coefficient. And so any of these add molecules that hit that edge are going to immediately incorporate and become part of the edge. And if there's enough of these steps, if they're closely spaced enough, then every molecule has time. It bounces around on the surface for a while, diffuses around, and it has time to hit one of those edges. and it'll stick or become incorporated into that edge. And so again, alpha will be 1 if you have lots of steps, closely spaced steps, and that sort of makes good sense. Okay. So what you're left with is faceted surfaces where these steps are either very far apart or non-existent. And of course, the simplest case is if you have no steps at all. So you have a perfectly faceted surface. And there are 2, basal and prism facets. And on those surfaces, alpha is much less than 1, which is why they're faceted. And so it's just absolutely essential to this problem that you understand alpha basal and alpha prism, because that defines the growth. I mean, if you know alpha and everything about it, then you've defined the problem, and you can predict or calculate what the growth velocity will be at any surface supersaturation, and you're effectively done for faceted surfaces. But if you don't understand these, then you're done too. You go home. I mean, you just close your computer and stop, because you can't do anything anymore if you don't understand those. So we have to do that first. That is the next step. And so we'll do that. And so that gets us to nucleation of terraces. So now our faceted surface has no steps. And we have more processes. Molecules will deposit and they'll sublimate away. And they'll wander around and surface diffuse for a while. And they will form new molecular terraces. Okay? And so now you come up with the Gibbs-Thompson effect applies to these terraces, and you find that the equilibrium vapor pressure depends on the size of the terrace, and smaller terraces are unstable to sublimation, and that's just because there's not very much binding those small terraces together. Once the size of the terrace is infinite, so this edge becomes a straight line, then the equilibrium vapor pressure is just the saturated vapor pressure for ice, and then you've got a stable crystal. So it becomes a nucleation problem. In order to make a terrace, you've got to first make one big enough that it's stable. When you put 2 or 3 molecules together, that's unstable, it'll just fall apart, and at some point you have to make enough of a big enough terrace that it will be stable and continue to grow. And that requires some minimum size. And so it's a classic nucleation problem, in this case, 2-dimensional nucleation problem. And this has been known for a long time. This was all worked out between the 1920s and 1950s. So by the 1950s, it had pretty well solidified as a theory, terrace nucleation theory. And it's in any book, crystal growth. It's a whole chapter. It's a standard thing. And I will not try to derive it, but there is a solution, and this is it. So you have to do a lot of statistical mechanics of these terraces, and they are coming and going all the time. At any given time on the surface, there are terraces of all sizes, islands of all sizes, and they are all coming and going randomly. And then you have to just ask, what is the probability that one of those will grow large enough that it will then continue to grow and make a new terrace that is stable? And the answer you get is down here, and there's alpha, and it has this characteristic exponential form, okay? And sigma surf is the surface supersaturation, okay? So if the supersaturation is 0, nothing grows, everything is just stable. Supersaturation has to be positive for growth. But if it's very small, then this exponential is really, really very tiny. Sigma 0 is this nucleation barrier, and it is basically based on the size of the molecule, kT, and the step energy. And this is what I call a robust result of the theory. If you kind of look through the theory and the derivation of the theory, this parameter always comes out. It's no matter what you do, you can vary a lot of the assumptions in the model, but this looks about the same. You can put a constant in front of there. There's a geometrical constant in here, which is of order 1. Because A, the size of the molecule, what does that mean? The molecule is not, it's not a sphere, so there's a bit of a constant there. But we're going to ignore that constant, call it 1, and just absorb that into the step energy, which we're going to measure, so we don't really know what it is a priori. And so that's what I call a robust function of the theory, feature of the theory. This A out front is just a number, a dimensionless number. And A is comes out of the calculation too. It usually has a weak dependence on supersaturation, like supersaturation to the 5/6 power. And we're going to ignore that too. This is a very strong dependence on supersaturation. A, we're just going to take to be a constant. And by a constant, I mean a constant as independent of surface supersaturation. All of this depends on temperature. So this is all just to be meant to be at one temperature. Okay. And the step energy, not everybody's familiar with the step energy, but it's really just a standard product of the crystal energetics. And you're all familiar with latent heat, of course, the energy per unit volume or per unit mass. And that's the energy to vaporize the crystal, 3 dimensions. There's also surface energy, surface tension. And that's an energy it takes to break the bonds and make more surface. So if you have a block of ice and you want to break it in two, you've got to break a whole bunch of bonds. And the number of bonds you have to break is proportional to the area of the surface that you're going to break. And so we say that you have to, in order to break the crystal, you have to make area. And so that involves a certain number of bonds, which is proportional to the area. And so the surface energy is an energy per unit area. And the step energy just completes the progression. We have a terrace, and we're just going to take that terrace and just cut it in two and break it in two. We have to break some molecular bonds to do it. We create a perimeter. And all of this is one molecule high, and it's sitting on a faceted surface. That requires that we break some of these molecular bonds, and we make a length. We make perimeter. And so the step energy is an energy per unit length. Okay? And these are equilibrium properties of the crystal. In principle, if you have a good model, molecular model of the crystal, you'd only need a unit cell. You can calculate the latent heat, you could calculate the surface energy if you knew what the surface looked like, and you could calculate the step energy if you knew what the step structure was. Okay, so for a simple crystal where you really understand what the thing looks like, you can calculate all these in equilibrium, and it's just simple stuff. Okay, ice is tricky because you don't really know what the surface looks like very well. But anyway, this is the result we get. As an exercise for the reader, but you can look this up in any crystal growth book. Pretty standard stuff. Been around for a long time. Now, does it apply to our problem? Because just because you have a theory doesn't mean it really works. Especially with an unusual surface like ice, which is a little different than silicon and the usual things people work with. So you have to measure it. So the easiest way is you just watch some crystals grow. And you measure the growth velocity as a function of the supersaturation, because you can do that. And this is a case of you start with a tiny crystal and you watch it grow at some supersaturation. You change the supersaturation, you can measure the growth velocity, and you just plot it. And there it is. And this curve has this functional form to pretty reasonable accuracy. It's certainly not linear or anything like that. It fits really nicely to that. So we have a theory, and it seems to work. This sigma 0 is an adjustable parameter, as is A. There's some, A is also an adjustable parameter, but in terms of functional forms, it fits nicely. Okay, and if you measure this sigma 0 by doing a fit, you're basically measuring the step energy. So we can extract the step energies from these measurements, and that's usually how one measures the step energy. Just like when you measure the surface energy, surface tension of water, the way you measure that, the most accurate way to measure that is to look at, or one way accurate measure is to look at the nucleation of water droplets. It's a similar thing. Okay. And this all works, by the way, if for dislocation-free crystals. These are perfect facets. And amazingly enough, that when you do these experiments for a long time, you find that ice looks an awful lot like it has no dislocations that really affect the growth. I mean, the idea of a perfect crystal is fiction. They tell you that right away in crystal growth business. No such thing as a perfect crystal, but it behaves an awful lot like a perfect crystal because it doesn't seem to have any dislocations that affect the growth. This just fits this curve perfectly. There's a question up there. Oh, oh, very good. Okay. Okay, so at least when you do some experiments, it seems to fit. I like to talk a little about the experiments because I do this a lot. So I'll describe some of the experiments to you. This is my favorite way to measure growth rates in the lab. So you start with a chamber that looks like this. It's a small chamber, and you've got a top surface that has one temperature and a bottom surface that has another temperature. This surface is covered with frost, and so that's the ice reservoir. And then you drop a test crystal all by itself on this bottom surface. And if you remove the test crystal, you can calculate the supersaturation inside that at this surface, because it just you don't measure supersaturation in the lab like ever. You only calculate it. You have to model it. That's unfortunate, but that's the way it is. So you put this test crystal in an environment where you know the supersaturation because you know these two temperatures. And we're going to measure the basal growth rate using white light interferometry. This is just it's such a fun technique. So you have a crystal sitting up here in the substrate. You have a lamp, just an incandescent lamp, shine it through a slit, and it goes up through the microscope, and it hits the substrate. That light hits the substrate, and it bounces off two surfaces, this surface and this surface. And so in each surface, there's an index jump from glass, or sapphire in our case, to ice, and ice to air or vacuum. And those two index jumps are comparable in size, and so you get two reflections, and they interfere with one another. And that interfering light comes down, and you send it through a transmission grating, and then onto a camera, and here's the result. The colors here are real. This is just a color camera. And the fringes are just these interference fringes. And so from counting those fringes, or from the spacing of the fringes, you get an absolute measurement of the crystal thickness, which is pretty accurate. And if you want to know how thick that crystal is, you just take roughly the number of fringes there times the wavelength of light, and that gives you the thickness. So this is maybe a 10 micron thick crystal. And when it grows, these fringes will slowly move. They get smaller and they move to the side. And you can get really high signal noise and measure very small growth rates this way by measuring the movement of those fringes. So it's a really nice technique for measuring very accurate velocities, even very low velocities. So here's just a typical measurement, and I'll tell you why I'm showing you all this in a second. But the idea is you measure, here's the crystal height, or the thickness and radius. It's a hexagon, but we'll call it a radius, as a function of time. And here, there's two for the radius and the thickness, and then there's the supersaturation. And so for this crystal, I started over here at t equals 0, and you adjust, and you get it so the supersaturation close to 0, and you know where 0 is. And here it's just growing very slowly, and you get it all set up, and it looks good. Everything's set up. It takes a couple of minutes, and then you just slowly turn up the supersaturation by changing those temperatures, the reservoir temperature. And here's the supersaturation going up, and here the crystal's growing. Okay, and then you can take the derivative of those curves and get velocity as a function of time. And the basal growth is kind of smooth because that's done using interferometry. The prism is quite a bit noisier because that's just imaging. And then we can take these velocities as a function of time, and we know what supersaturation is as a function of time, so we can look at the velocity as a function of supersaturation, and you get some curves. And then you just do plug that into the formula, and you get alpha as a function of supersaturation. And that gives this curve for the basal down here. And now you have to recognize that even though you've pumped all the air out, this is at 0.005 atmospheres, there's still diffusion correction. And so the supersaturation you think you have is actually about half of twice what it really is. And you can calculate that, because if you know the size of the crystal and the velocities, you know how much mass is being added to that crystal. And there's just, you calculate it. There's a formula for making small corrections to the supersaturation at the surface. So this is the supersaturation at the surface, and after you correct it. And that gives you this curve, which looks like nucleation limited growth. And this took a long time to get to work. And there was a previous literature on this for many years, and the experiments were just not done with sufficient care, and so people were getting answers all over the place. And you really had to work at it. I mean, we spent about 10 years on this, just slowly perfecting all this. There are a lot of systematic problems. This diffusion correction, you got to get it right. People didn't always do that. Sometimes the substrate affects the growth because the prism facets actually interact with the substrate. You've got to model the supersaturation from those temperatures. You got to get that right. If you have chemical impurities, that can be a problem. And we've learned, as have others, that you want to use nice fresh crystals, and you only want to grow them once. If you melt them, if you evaporate them down, they get covered with crud. So we always make a crystal, drop it on there, and measure it all in a few minutes. And the crystals were freshly grown right in the lab. So everything is as clean and fresh as possible. You do not want to make a crystal and let it sit around for half a day and then measure it. That's a terrible way to do it. And you have to worry a little about imperfections. Some crystals have imperfections, but not very many. And it took us a long time to get this right, but I think we have now. We like sapphire because it has high heat conductivity. So it, see? The problem is that if we have glass and we change the temperature of the whatever it's attached to, then we change the temperature of the edge, but it takes a while for it to equilibrate. Sapphire is very fast because it's very high heat conductivity. So we have a copper plate and we glue a piece of sapphire to it. We change the copper plate and we measure the copper plate. And with glass, we're never quite sure that it's the same temperature. It will be eventually. But with sapphire, it's almost instantaneous. So. Yeah. Thickness of the. Step by step. I don't understand. Oh, no, this is not that resolution. Other people, it is possible, and there's some Japanese group that can measure individual terraces. It's quite a feat, and yeah. We are just 1/10 of a micron, or something like that. Well, actually, we can measure velocities down to like a nanometer per second, but we are not seeing individual terraces. Okay, so we do this a lot. Grow lots of crystals. Here's a sample. We got velocity as a function of supersaturation. This is this curve, and we can extract a sigma 0 from that. Here's 23 different crystals. We measured sigma 0. You see there's some scatter, and we do a fit to that, and let's get a number and an error bar. And that's at one temperature, at -12 or something. I forget what it is. But we do this over and over again with every temperature, and we try to do the basal and the prism facet as well. We've actually done different experiments. There's the interferometer experiment, and we also have a second experiment where we just look at growing crystals on a sort of hydrophobic substrate, so we don't have a lot of substrate interactions. So really, we've done this very carefully, I believe. And this is what we get. So here's temperature, and here is sigma 0 in percent, and an A. Okay, so A looks like it's 1 for the basal facet, maybe not 1 for the prism facet, and we get these numbers. Okay, and what do you say? There it is. It's we spent an awful long time doing this, and so really studied the systematic errors and grew a lot of crystals and threw away a lot of data before we finally got everything cleaned up and working. So this is our answer, and this fully defines the growth of the facets. Okay, so if you give me a temperature and a surface supersaturation, I can plug it into this formula and tell you what the growth rate will be. And so you don't need any more than this. This is all the information you need to understand the growth of the facets. And you don't need to understand where these numbers come from physically, necessarily. You just, once you know the numbers, you're there. It's like the index of refraction of water. You don't need to know why it is what it is, but you can measure it, and then you're done. So yeah. Yeah. I'm gonna tell you now what I think is going on here, and I can tell you what's going on here, and this is a mystery to me, and I have some things to say about that, and I have said them, and I don't really believe them very much, so I'm not going to talk about it. No, I mean, it's something. I've certainly looked very carefully at that. I would love this to be 1, because that makes beautiful physical sense. But when you look at the curves, it's not. And so, well, let me keep going. Okay, so first I've got these data, and I'm trying to convince you that it's right, and I'll show you a couple kind of what we experimentalists call a reality check. Things that are supposed to look right, and if they don't look right, you're puzzled. And here's one: it's just the convergence of alpha of sigma. And I'm just going to look at it for the basal facet where it makes the most sense, but it's a nice result. So here we're going to plot alpha on a log scale versus 1 over sigma surf. Okay, we got all that data. We can plot it however we want. And this functional form will be a line. Okay, and if we extrapolate that line to 0, we're just extrapolating to infinite surface supersaturation. And none of this was constrained to go to alpha of 1. You measure a velocity and you measure a supersaturation, or you model the supersaturation, you measure the velocity, you divide the two and you get a number out. And the number does not have to go to 1 in any particular way, because you just measured those two things and divided them. But you look at the curves, they are lines. Each temperature is a different line, but there are lines, and they all converge rather nicely on 1 to reasonable approximation. And that's just exactly what you would expect, because when you take the supersaturation to infinity, you're making lots and lots of terraces all the time. And so there's just countless steps on the surface, and you get a kind of a roughening transition. So the surface becomes rough, and you expect alpha to go to 1. And so lo and behold, it does. And it's a beautiful result, because it was not constrained to go to 1 in any way. And it does, and that makes good sense, and I like that. This is not going to 1, and I don't like that, but it is what it is. So we'll talk a little about that, but not much. Fortunately, this little piece down here is not going to change the story very much. It's a little add-on, so we're going to ignore it for now. So let's look at the sigma 0 here. Okay, and we're going to convert that, I believe we're going to convert that to step energy, because we know how to do that. We just take sigma 0, plug it into the formula. So here's step energy, and that is the fundamental result, of course. The step energy, as I mentioned, an equilibrium property of the crystal as a function of temperature. And so this is where you should be able to calculate it if you really knew the structure of this crystal surface. And so it's changing as a function of temperature. And so something's going on. I mean, the latent heat doesn't change much as a function of temperature, and the surface energy doesn't change much as a function of temperature, a little bit, but this changes a lot as a function of temperature, and so it's different. And so what's happening is the surface, say the step energy depends on the structure of the surface, the molecular structure of the surface, and that seems to be changing a lot. And the way you can see that is have look at the surface pre-melting. When the crystal is very cold, then it looks a lot like the ball and stick model of an ice crystal. But when you get warm, the top layers are less bound, and so they start to become amorphous. And there seems to be quite a lot of evidence for this from lots of surface probes at the ice vapor interface and lots of molecular dynamic simulations. They pretty much all show some kind of surface pre-melting. Okay, here's now what they show is another story. These are measurements of the thickness of this pre-melted layer as a function of temperature for all kinds of, this is just a meta-analysis, and I can't remember where I got this picture, but I can find the reference if you want to see it. But these are all different surface probes, and it's just a mess. But there is some general trend. But I will tell you that if you study this a little bit, you'll find that almost all these measurements, they're not measuring the thickness of the quasi-liquid layer. They're measuring some proxy of that, okay? And it's just not exactly clear how the proxy relates to an actual thickness, or even what the actual thickness is. I mean, this is a diffuse boundary, and the molecular dynamic simulations do show a kind of nice, just very specific boundary, but maybe they're wrong, I don't know. At any rate, so you would expect an awful lot of scatter in here. Plus, this is every measurement, ever made, and some of these are not good measurements, I suspect. So, nevertheless, it is generally accepted there's surface pre-melting in this situation, and that changes the structure of the surface a lot with temperature. Okay, obviously. And if it exists, then it changes the structure of the surface, and that could explain this. Okay? Does it explain it? Well, it could explain it. Probably explains it. I'm not going to tell you how it explains it. I don't know that. But nevertheless, let's go back, and we got our step energy. Let's consider the step geometry. This is a picture I like to have in my head. Remember, I'm trying to just kind of get a physical picture. Excuse me. So the simplest structure of a step is just a simple step. Okay, so one molecule high, Terra step. And what would the step energy be in that situation? Well, we've added surface. We added a step, but the step has a surface. So we know the surface. If we know the surface energy, then we've added one molecular height times the length of the surface energy, and that gives you a measurement, a calculation of the step energy. And it's just this. It's just the surface energy times the height of the step. And that gives you some number. Now that's an extreme case because the actual step is not going to be so abrupt. But we might, and that number is out here somewhere, around here. And so the picture that I like to think in my head is that if you go to very cold crystals, no pre-melting, nothing, just a very, very cold surface way out here, minus 100, then yeah, this is starting to look like what a real crystal looks like. It's got an abrupt step. It's very, very cold. So, and so, yeah, that's kind of an asymptotic number way out here. That's the way I think of it. Now, if you make a more gradual step, using the same just adding surface model, if you make the step more gradual, you've added less surface. This is the worst case. You added the most surface for a step. Here, as you make the width of that step bigger, the surface you add goes to 0. And so the idea is that as you increase the temperature, this just very simple picture, no real physics behind this. But as you increase the temperature, the surface structure changes, and that step gets smeared out. It just smooshes out with surface pre-melting in some way we don't understand. Okay, so that kind of makes sense. I mean, it could explain it. It's not a model. It's just trying to show that it's not crazy that it would do this. Okay, and the step energy is, like I said, I like to say, it's an equilibrium property of the material. So in principle, one should be able to measure that some way other than this, like with molecular dynamic simulations. That would be nice. We're not there yet, but in principle, one could verify this by measuring it. So the idea, the physical, just very qualitative physical picture, is that low temperatures, you get a simple molecular step, and you're way up here in this region at some asymptotic, you don't want to extrapolate your data too much, but nevertheless, that's what it's. And then as the temperature goes up, the surface structure changes, and pre-melting or whatever phenomena just smooths that step as it relaxes. Okay. So that's the explanation that I have in my head for why you see this change with temperature, which is pretty substantial, 2 orders of magnitude. Here's another one I like, another kind of reality check. So the picture I have is that there's this quasi-liquid layer, and there's a step. And if you ask, well, where's the step? Well, it's not up here at the top. It's here at it's at the crystal. And so what you really have when you have a terrace step is it's a step between the ice and the quasi-liquid layer. Well, that looks as the temperature gets higher, the quasi-liquid layer becomes thicker and more pronounced. At least that's what we think. And that's what the community thinks. And so this step starts to look an awful lot like this step, which is just water and ice. And so I started looking around in the literature to see if anybody had measured this step. And the answer is yes. And a long time ago, 1958, was the best I found in a conference proceedings. It was really a very obscure paper. A couple other papers as well, but not a lot of work done on this. But I really liked this paper. Hillig did a beautiful experiment, and it looked very clean and pretty. And so I replotted the data and drew the theory curve through it, and you get a number out of it. And it has been reproduced enough that it's sort of believable. And here's the number, 5.6 times 10 to the minus 13. And that's what this step energy is for ice water. And if it's plotted on here, it's right here. That's that red line. And lo and behold, as the basal step, ice vapor, as you increase the temperature, it gets close to that. Now, this is a log curve, so if you want to extrapolate that to 0, you got to go pretty far out. But nevertheless, as the quasi-liquid layer gets thick enough, these start to look the same. And that I thought was just very pleasing because you get the same number, more or less, for these two. And you should. I mean, if there's a good physical reason that you should. Now, what about the prism surface? That just goes to 0, or at least it's going down fast. And lo and behold, if you look at ice, here's a piece of ice that this person picked up out of a pond, and you can go to out of any freshwater pond and you can find crystals not quite this nice. But this has a very strong basal faceting in it, but there's no prism faceting. And if you grow crystals in the lab from liquid water, you never get any prism faceting. And so this seems to have no step energy at the ice-water interface, and this seems to be going down to 0 as well. So this whole picture of this correspondence between these two surfaces seems to hold water, if you will. And so that looks good. So I'm saying this is right. Okay, I'm going to go with that. And like I say, I've been working on this for decades now, and you start making more and more measurements, and it starts to really converge. And after a while, you start to believe it. And so now let's compare with the Nakaya diagram. Well, Nakaya diagram is absolutely correct. There's no possible way this can be wrong because lots of people have done this, and everybody gets the same answer. This is brand new stuff, so it's not nearly as firm a footing, but we can compare the two. And so what you find is at high temperatures, this big difference here that means that there's basal faceting and no prism faceting. Not so much. Well, you get a little prism faceting from this, but never mind that. You get plates. And yes, you get plates. That's good. But the rest of it's a mess. It doesn't look at all like this. You have a single transition from plates to columns, and that's it. So total disagreement except for, at high temperatures. So here we went to great trouble to measure the growth of facets. And like I said, this completely defines the facet growth. If you believe it, and we just don't get the right answer at all. Okay, so that's a problem. It's been a problem for a long time. People have been trying to solve this for 75 years. Now we know it's not diffusion limited growth, because diffusion limited growth does not give you plates and columns. It gives you dendrites, but not plates and columns. It has to be anisotropy in the attachment kinetics, and so we need something new. This is not enough. And so, you know, what the heck? So these were grown in vacuum, and these were grown in air, and maybe that has something to do with it. And, you know, there could be impurities. There's all kinds of possible things I thought about. And it was a real puzzler. And then I made what I... Yeah, that's what I mean. That's right. And it's not even a perfect vacuum. It's got water vapor and a little bit of air. No, it's 0.005 bar, say. It's really hard to get rid of all the air without pumping the crystal out as well. Yeah. It's low enough that the diffusion correction is pretty small. And so if you grow in air, you've got to worry about the difference between the supersaturation where you make it and at the crystal surface. And it's a huge correction at 1 bar. And it starts to be tolerable at some millibars. So we can do that, okay? So then I made what I think was a sort of key observation in my brain as time went on, is that whenever you saw these really anomalously, these large morphological anisotropies, thin plates and columns, there's always a sharp edge. Okay, these crystals are very thin and flat. Here's a side view of a crystal. And if you look at this one, this is a facet, okay? And this would be a facet. And so there's a facet in there. And similarly here, it's a little easier to see. This is a facet. That's a faceted crystal. And but it's very thin. And so in both these cases, you have a very thin, wide facet, okay? So there's not a broad facet, like an infinitely large facet is one thing. These are very skinny facets. And the radius of curvature of these things is of order a few microns, okay? And so in the fastest growing cases, there's a last terrace, okay? If you look at the surface up here, that's a faceted surface, and the faceted surface is defined by that last terrace, okay? There's the highest terrace. What happens below that is not so important, but there's a terrace on top, which is flat, molecularly flat, which is why it's faceted. And that thing can be like 1,000 molecules wide, okay? Not less than that, and it can be more than that, but it's pretty narrow. And now, that's not very narrow if you're talking about nucleation processes, but it's pretty narrow. And you never see those narrow facets in these low pressure growth ever. So something funny's going on when you see these things. And so I sort of decided that maybe we got rough surfaces that have fast kinetics, and faceted surfaces are terrace nucleation, but maybe narrow facets are just different. Why would they be different? Well, let's not worry about that. Let's just say they are. So I'm going to make a hypothesis, which I called structure-dependent attachment kinetics. Turns out a terrible name, but nevertheless, it's sort of stuck. And I actually published this 20 years ago, so I thought about it for a while, and I've come to believe it. So the hypothesis is that if you have a large facet, okay, then you have normal terrace nucleation, and we now have measured sigma 0. We're all done. That's good. But if you have this narrow facet edge, then for some reason that I will specify later, but we don't have to worry about it. This is a hypothesis. We're going to say for some reason that has a higher alpha, and we're going to model that by saying it has a smaller nucleation barrier or a smaller sigma 0. That's a good way to model it. The only way, that's just a parameterization. If alpha has to be high, then if you parameterize it in the same way, sigma 0 has to be low. It's not going to have the same functional form because there's different physics involved, but we're going to call it that. We're just going to say sigma 0 is reduced. And that's a hypothesis. We're just throwing that out there, making that up, okay? And that immediately, now we're going to assume it's true and see where it takes us. The first thing that happens is you get what I call an edge sharpening instability, which is a lovely thing. So here is a substrate with a crystal growing on top, a bit block, and the c-axis is up. And so if you grow it slowly, you will nucleate in air. You will nucleate new terraces at the corner here, because that's where the supersaturation is highest. And these terraces will grow, and these surfaces will be slightly concave, which is well known. And so everything's just hunky-dory as long as you grow it slowly. But now I'm going to say that these narrow facets at the top are a little bit unstable. They will start to have a smaller nucleation barrier. And what happens is, as you grow the crystal faster, this top terrace gets narrower and narrower just by normal means. And if the nucleation barrier goes down, as this happens, then this is going to run away. Okay, so if this basal surface has this effect, then as you grow it, it will eventually undergo an instability, and this thing will get narrower and narrower, and it'll just take off until surface energy prevents it from getting too small. Similarly, if you allow that this kind of hypothesis on the prism facet, then you get a plate crystal growing from that edge. So there's these two possibilities, and in both cases, it's a growth instability. It's not the Mullins-Sakirke instability. It's totally different. It involves the attachment kinetics. It's not just, but it involves diffusion. You need diffusion to make it work, because you've got to be making these terraces at the corners, and also this has to grow more slowly than this. Lots of reasons, we can talk about it, but basically you can have these two possibilities, and in both cases these are going to be very thin edges, just like we saw, and a micron seems to be about where where surface energy kicks in and makes them not get thinner, and that's about right. And you could have this okay. So you get thin edges for free off this because it's an instability, a weird growth instability, a new growth instability. And if you allow these to be temperature dependent, sometimes, so at say at one temperature you go in this direction, but if you change the temperature slightly, it flops and goes over to this direction. So it's always unstable, except sometimes it goes here and sometimes it goes here, and in the middle it just kind of can't decide, and there's an intermediate state. But most of the time, it just goes bang on. So you can get these very abrupt morphological changes. And what did we see in the Nakaya diagram? Abrupt morphological changes. And you know, it just makes sense. I mean, why do you ever get an abrupt change in anything? Because of instabilities. That's how this works. And and also, if you try to do any of this in vacuum, it doesn't work. It just needs to have diffusion as part of the deal. And so I really am thinking this is the missing link, okay, was this that narrow facets are just different than broad facets, and that produces this instability, and that's a big part of the deal. Okay, and so I like it. It really works. You can make some measurements and try to test this hypothesis as best one can. We grow needles, plates on needles, and you can try to it makes certain predictions as to what will happen. And in particular, if you look at, say, a crystal like this, the prediction is that the basal surface over here is a broad, the top facet here is a broad facet, and so it'll follow the normal terrace nucleation. And over here, it's a narrow facet, and so it's going to have a lower sigma 0. And similarly in the other direction for needles. And we can't really do this exactly. We can't look at the basal growth and the prism growth absolutely, because this is an air and you cannot predict the surface supersaturation in air very well. But if you look at the tip right over here, if you look carefully at that tip, you will find there is over here a very small but finite basal facet and an even smaller prism facet somewhere. And those facets, small as they are, they define the growth of the crystal, because everything else, alpha is 1. And that's the only place where alpha is not 1. And the supersaturation at the tip is whatever it is, but it's the same for both of those little facets. And so we can look at the ratios. Okay, I call this a witness surface. So we're going to assume that the basal facet is normal terrace nucleation, and we're going to measure the prism facet. And we can do that. It's just looking at ratios. And you get something like this. So here's we're looking at these plates. The basal growth, we just measure the basal growth, and we say it's going to fall on this line. That's the terrace nucleation model. I smoothed it out a little bit. And so we just put those points on there. That allows us to measure indirectly the surface supersaturation. So here at 64% is the saturation at infinity, and I measure the basal growth, and I find, oh, the saturation of the surface is only 1.5%. That is not at all unreasonable that it would be that way. And so I'm just going to put those lines, those points on that line, and then see where the prism comes out, and it's much higher. And so that kind of makes sense. It fits. But the other thing, though, the one finished, is that when I do that, this goes to 1. It does not go way up here. It doesn't way down there. It goes to 1, which is kind of where it's supposed to go. So. Yeah, it's hard to explain, but we can talk about it later. I'm just trying to... You know what I mean? You can spend a half an hour on this. I'm trying to give you the gist. We are basically just trying to use these data to see if it fits the model. And one can turn this around, for example, and if you look at the prism alpha, okay? Well, when you get up here, the facets break up. Okay, when the facets are breaking up, that tells you alpha is close to 1. So we know alpha is 1. Just by the morphology. And we can say, well, if alpha is 1, then what does the basal alpha have to be? Because it's a plate. And actually, the numbers lie on that line pretty well. So here I inverted the thing. I put the dots on this, and I plotted that as data. I could also put these data at 1, and I would plot it down here. So it's a consistency check. It works. Okay, and the reason it works is just I'm saying this doesn't go crazy on you. It just goes to 1. We can do the same thing with the basal surface when we're looking at needles. Oh, the model's a little harder because of that A not being equal to 1, and I'm certainly not going to go through a lot of details on that. But it again sort of fits. When you look at the basal surfaces, it goes to 1, like it should. And you put it all together, do this at all different temperatures. We love taking data. And you get what I call a pair of S-stacked dips. Okay, the surface structure-dependent attachment kinetics produces these dips. So here is this line, for example, at high temperature. This line is the normal basal growth. This is the normal prism growth. But if you look at the growth, when you see, say, hollow columns now, that gives you a dip like this. And similarly, if you look at prism growth, you get a dip when you get very thin plates. Okay, and this is what you get for broad plates. Okay, so these lines are just smooth lines of what normal facets grow like, and this is what thin facets grow like. Now it's all a little bit circular. We assumed that the thin facets did something, and then we sort of went through and saw that they did the right thing. But these curves are not made up. These come out of the data. So this kind of tells you the extent of the dip, and it gives you a picture of what's going on. But mainly, it's just kind of, it supports the model. It all kind of hangs together. Sigma 0 doesn't go to anything below 0 or anything. It goes to 1. It all kind of works. And we see that the basal facets grow anomalously fast near -4, and the prism facets are anomalously fast around -14. And so that's just the Nakaya diagram in a convoluted form is all that really is. But we will press on. I'm getting to a point here. So we started with this, where we have these are broad facets, large facets. That does not cut the mustard. Okay. It doesn't work. Doesn't fit the Nakaya diagram at all. But if we include this S-stack model and the S-stack dips, now we have a dip here and a dip here, and just from the data. And lo and behold, it now works pretty well. We get columns and plates and columns and plates, and so it all works, okay? So what we ended up with, what we did is we put in a relatively simple hypothesis, complicated enough, and then we sort of followed it through, and we got a crazy amount of complexity out, and just beautifully, the crazy amount of complexity we got out fits the Nakaya diagram, and it sort of agrees with all the data we have, and so, you know, it kind of fits, it works. It's speculative, but nevertheless, we're making some progress, we believe. Very semi-quantitative, based on observations. And so this is our model, that just something about these narrow facets is just weird. And you assume that, and you can now explain everything. Okay, that was the missing link. Okay, but what is going on? Why do you get this? What's the physical mechanism? I thought about that for a long time, and it's hard. But here's what I got. Okay, I think this is the first time I really started to believe it, and so you don't have to try to make something fit. You just have to ask, what happens if you have a plate? So here's a plate. It's got basal surfaces, and it's got an edge. And we're going to make it a narrow edge. So again, this last little bit here is only 1,000 molecules, the last terrace. And we're just going to let that plate sit there quietly. It's low supersaturation, so the basal surfaces aren't going to grow at all. And it's going to be round. It's going to be just enough supersaturation to give you a nice rounded edge in equilibrium, quasi-equilibrium. And that'll just sit there for a long time, okay? Just a prism surface in here, but mostly just round. So now we're going to turn up the supersaturation. We're going to start with that, and we'll turn up the supersaturation. Well, what happens? Well, the prism facet is there. The corners will grow because they're rough. And the corners will grow until the Gibbs-Thompson effect prevents them from growing anymore. And a prism facet will develop. And it will not grow because now it's a broad facet, and the broad facets are fairly slow growing. But the surface energy is now out of equilibrium because we've increased the supersaturation. It would like to be round, but now it's sharp. Okay, so if you imagine that this was liquid instead of solid, well, this would pop right into a liquid form right away. So there's a force, a thermodynamic force, which would like these molecules to push over onto that surface. If they can, if it was liquid, they would just run right over there and you'd get a nice round surface. But it's not liquid, it's a solid, so they can't move. But now I'm going to say, well, what if I add a little bit of surface pre-melting and I just allow some of these molecules to move, okay? And they should eventually. If you make it more like a liquid, they'll start to move. And this prism facet is still very small. And if you move some of these molecules, add molecules onto the surface, you will increase the add molecule density above what it would be for normal terrace nucleation. And that will enhance the terrace nucleation. We've just had an extra supply of add molecules that's just not coming from the normal absorption and sublimation. And so you will get a lower sigma zero, effective sigma zero, but only on narrow prism facets because these guys, there has to be a small area there. So this would produce the S-stack effect, I think. Maybe. It's, you gotta do it, you gotta keep moving in this game. So now we're gonna say, well, what's going on? Well, let's add pre-melting to this. This is not a new idea. Throwing pre-melting in to save the day and people have been doing this for a long time. Because you got to have something that changes the temperature, and this is about it. So if you have no pre-melting up here, no pre-melting, then there's going to be no diffusion, surface diffusion. It's solid. It's no surface diffusion. Nothing's going to happen, and so you will not get any S-stack effect. Okay. If you have strong pre-melting, like this, then you have lots of surface diffusion. This thing's practically a liquid. But how is that going to affect the nucleation? There's so much mass there already. You're going to squirt a little extra on, it's just not going to do much. But there's an intermediate where you've got, it's like this. Okay, so there's not too much there already, and if you now allow some of these molecules to spill over, you might have enough molecules to reduce the nucleation barrier, and it'll grow faster. And that's just at one specific temperature that's going to happen. So at low temperatures, nothing. At high temperatures, nothing. But right there, that's the special spot. That's where the surface pre-melting is just starting to happen. And that's when this whole thing starts to work. So we're going to do one last thing is we're going to postulate that the prism pre-melting is going to happen at -14, and the basal pre-melting is going to onset at -4, and that will give you the S-stack dips where you want them. And like I said, this is not an idea that I thought of. This is there's some papers by Kuroda who talked about using surface pre-melting in a similar way. And so anyway, so it sort of makes a little bit of sense, maybe, that you might have this work. So I know you're sitting there going, well, this is crazy. This is way too complicated. What are you talking about? This is nuts. Okay, so I made some assumptions. I just assumed that the narrow facets were different. That was really the start. The start of this nonsense was to say narrow facets are different. That gives you these dips, and that can explain the Nakaya diagram. And it seems plausible that this would happen. I think the mechanism is plausible. It's certainly not a solid theory, but you start where you can. And it also explains why you get no anisotropy at low pressure growth, because none of this can happen at low pressure. And so basically, I put in a little bit of assumptions, and I get a crazy amount of weirdness out of that assumption. And miraculously, all the weirdness I get out seems to fit all the data and Nakaya diagram and everything. And so it just kind of, wow, it actually kind of, it's crazy, but it's not totally crazy, okay? Some parts of this I think are right, okay? Now, the great part is that this model makes tons of predictions. I mean, you've thrown a lot of stuff out there. And so you can do targeted experiments, and the data I showed you just now is one targeted experiment. And the idea of that is just to see whether the experiment supports the idea or does not. And the idea did support, the data did support the model. Didn't prove the model, they just support it. They didn't say, no, that's wrong. They say, yeah, it makes sense. Now, what's the alternative? How else are you going to do this? People over the years have made other models of the Nakaya diagram, and with more data, especially with the facet growth data, you can throw them all away. They don't fit at all. So this is it. This is the best model we have. The only alternative is what I call the something else model. In other words, well, it can't possibly be that. It must be something else. And the trouble with the something else model is it just makes no useful predictions. When you sort of make a model which is crazy, you at least say you can at least do lots of experiments to sort of confirm it or reject it. And so it's got that going for it. And so far, I've been doing everything I can, and it always seems to support it. So, like I say, I'm starting to think this might be even right. But time will tell. Come back in 50 years, and we'll know if it's right or not. So I will leave you with that. But before that, I think I have one a lighter picture, okay, about triangular snow crystals. So this is when you have this crazy theory, and you turn over here to something completely different and explains it, you think, well, that's cool. I didn't set out to explain that, and it kind of does. And so you start to think it really might be right. And so I'm going to talk about triangular snow crystals. These are exactly that. They're snow crystals that have a threefold symmetry. They were first documented in 1820. I love the name. An account of the Arctic regions with a history and description of the northern whale fishery out of Edinburgh. And so while they were, sailing away, waiting to find some whales, Mr. Scoresby was making sketches of snow crystals in very cold climates, and noticed at least one that was triangular, and documented that in his book. And since then, lots of people have seen triangular snowflakes. I've seen them. They fall out of the sky. They're usually not nice, perfect triangles, although this one was a nice truncated triangle earlier in its life, and these are truncated triangles. These fell out of the sky and onto my camera. These are some we made in the lab, just in free fall growth. And what's funny about these crystals is, I mean, people have been seeing them for 200 years, and it's just hard to explain. You know, why are all snow crystals why do they all have six-fold symmetry, except some that have triangles? And when you see them fall out of the sky, you tend to see more than one, so it's not completely random. They come in bunches, and so there's something deterministic about this. And there's some literature on this. People have described these in the scientific literature, and there's just been no good theory. And so I started thinking about this. Well, I've been thinking about it for a long time because it's been a puzzle. And so I want to look at when we make a plate on a needle. So we're going to start with a needle, and we're going to make a plate. Okay, formation of plates on electric needles. This is normal growth. After you make the needle, you make normal growth. Now we're going to look down on the column. Okay, and we're going to assume this theory is right, okay, that I just described. So there's this edge sharpening instability. So the column is sitting here and it's starting to grow, and this edge is going to be unstable to this edge sharpening instability. And it's not going to happen all at once. It's going to happen on one side first, obviously. And what happens is it will grow a plate on a small plate, a little platelet on the edge of that column. So it'll be precursor to this. And that plate produces thin edges. And the thin edges will grow faster than blunt edges. And so this growth will propagate around the crystal, around the column. And it will very quickly make its way all around and produce what is basically a hexagonal column. Not quite, not perfect. It turns out these hexagons aren't perfect either, but this is very small. This is some microns in size. If you grow it to a 0.5 millimeter, it starts to look a lot like a hexagonal plate. And so this is just a kind of a snapshot of what's going on. Is you start out with this edge sharpening instability, and it propagates around the column until you get a nice plate. And this instability explains why you get just really nice thin plates on the ends of these columns with very great regularity. But now we're going to change. Let's make this growth a little slower. So this instability just barely functions. Okay, it just barely works. So we start out with this, and we get our first little plate because it does barely work. But now, once this thing starts growing, it sucks water vapor out of the air, and supersaturation elsewhere goes down. And so this plate will grow out, and then it sort of stops growing as it gets pointed, and it will slowly start to make its way around the column. But it just, as this surface grows, it has so much time, it just grows into a point. And only after it points out does this final edge start to grow. And so if you just look at this and think about it for a while, if it grows very fast, fast growth, then it just propagates around very quickly and you get a hexagonal plate. But if it grows very slowly, it sort of does so in steps, and you can end up with a triangular plate. And lo and behold, we can make that. And this is the first ever on-demand triangular snow crystals. They've always appeared as kind of an accident, but not anymore. Now we can just dial it up and see it. And because we know where to go now. So here's some data. Once we had this model, we go to -14, where this instability is the strongest. And now here's just a run that took a day. We start out at high supersaturation, and we look at every crystal we grow. We grow a bunch of needles and look at them all, take pictures of all of them, and measure a triangularity parameter that just is how close it is to an equilateral triangle. So at first, they're all hexagons, okay, because they're all fast growing. And then as you go down and down, and then all of a sudden, they start to be triangular. And a middle triangularity parameter just means a truncated triangle. So equilateral triangle with the tips cut off. And so that's what you get down here. But at the magic supersaturation, you get almost 100% of these almost perfect triangles. Not quite. I mean, typical around 0.8, so a little bit truncated. They're not stable, by the way. If you grow them out, they will turn into truncated. The tips will go away and become truncated because this is not a stable growth. I always thought it would be, but it's not. And then eventually you get just blocks on columns and then just basic columns again. And when I first built this apparatus, one day I found saw one of these, and it was just growing off on the bottom somewhere, and I took a picture of it. It was the only one I ever saw. I just put that picture up on the wall, and it was just like, you know, what the heck happened that day that I had a triangle? And what happened in hindsight, that was years ago. In hindsight, I just happened to get this exact condition. And these are, you know, this changes a lot so I was usually over here or down here, and it's pretty uncommon to get exactly that condition unless you go look for it. So now I understand that. And so basically, this S-stack model and this edge sharpening instability will explain this too. So it's like, cool, good. No, I don't. Well, what's funny is that it's a little some, but the triangles don't stay. As soon as they get big, they want to truncate. They're very. You'd think that the normal instability, the tips would stick out farther, but no, that's not the case. You don't get anisotropy from diffusion. Diffusion likes round things. So I got a model. Crazy as it is, it seems to explain a lot of things, and it has a lot of weird features to it. But you know, you gotta go where you can go. And so I like to say it's not the final word by any stretch, but hopefully the start of an interesting dialogue. And we'll talk about that more in the next lecture. But overall, you know, when you start thinking about this, you can make some progress. So we're doing something, maybe. So I will stop there. Thank you.